Okay, we're going to continue on talking about AC power in this video, and where I want to start is this is the instantaneous power equation from the previous video with RMS quantities. So just so you can see where that equation came from, if we go back a couple pages, um, let's see, right here is where we wrote the instantaneous power using this, or the trig identity on the previous page, such that we could see that it was a sinusoid that was writing this constant amount here. Well, the V and I in this equation are all peak values. So if I just plug in square root of 2 RMS for V and also square root of 2 times I RMS for I, well, the square root of 2's will cancel out with the 2 below, okay, in both of these terms here. So what you see on the page that we began this video on is just this equation with RMS values instead of peak values. Well, the next thing I'm going to show you is some, or a derivation, okay, some algebraic manipulation that shows this instantaneous power in a different form where the terms have the components of impedance, resistance, and reactance. So that's on this handout here, which is also available on Polylearn. So here's the instantaneous power equation in terms of RMS for V and I, and I'll let you go through, you know, these steps here on your own. But the important result is here at the bottom, where we can show that instantaneous power is equal to these terms that all have a component of impedance. See the R here, and then X, which is reactance right here. So we can gain further insight into instantaneous power by looking at this form of instantaneous power. So first we're going to look at just these two terms that contain the real part of impedance, which is the resistance. And you'll see on the next slide that we factor out this I squared R. Okay, so after we factor out the I squared R, you know, we call these two terms PR of T. So this expression here is made up of PR of T and PX of T. Okay, that's what makes up the instantaneous power when it's in this form. So we're just looking at the terms that have resistance. And one thing you can gather from this is that this is a sinusoid, a cosine function that's centered on I squared R. So that's another way to show that I squared R is P average. Okay, we showed it in the previous video a different way. So two different ways to get the same result. Now here's some terminology to know that P average is also referred to as real power, and where that term comes from is that resistance is the real part of impedance. The units of real power are watts, just like in DC circuits, just like the power units in DC circuits. And this is really important here, that P average represents the amount of power absorbed by the impedance. Okay, resistance absorbs power in AC circuits just like in DC circuits. And then this is also important from a conceptual point of view and also a practical point of view, that P average represents the amount of electrical power that you can possibly convert into another form of power, such as mechanical. So if your impedance represents an AC motor, P average of that AC motor is the electrical power that's convertible to mechanical power. Okay, so that's what we gather by looking at PR of T, which are the terms that have resistance from our instantaneous power equation. Now here's the term involving reactance, so we call it PX of T. And here we call the amplitude I squared X, we call that reactive power, and we use Q. So here Q is standing for something different than it has previously in the course, right? Q is sometimes used for electrical charge, at least capital Q is sometimes used. Usually it's smaller case in EE and uppercase in physics. So you might have saw Q, capital Q, being used for charge in your physics book. In this class, just a few videos ago, we saw Q being used for quality of a bandpass filter. But here it's something totally different. It's being used to represent reactive power. See, that's the power that has to do with the reactance of the impedance, and reactance of the impedance, that has to do with the storage elements, right? The capacitor and inductor. Now look here, units of reactive power are VARs, and VARs is an acronym for volt ampere reactive. Okay, so here's your first, the first time you've seen a different unit other than watts for electrical power. Okay, and Q is the amount of power that's being exchanged between the storage elements of the impedance and the source in the circuit. And because this power is being exchanged, because it's not absorbed by the impedance, so therefore it doesn't stay with the impedance, well, it's non-convertible. Okay, power has to be absorbed by the impedance in order to have any chance of being converted into some other form of power from electrical. Alright, so let's see, the next thing we have here is that there's another power in AC circuit that's called complex power. And the first thing you need to know about complex power is that this power is made up. Okay, it's fictitious. It's not something that you can directly measure. Okay, we just make up this power because it's going to make it convenient to solve AC power problems by defining this complex power. And the way complex power is defined is that we use S to represent complex power, and it's defined as the voltage across an impedance, okay, in RMS, times the current across an impedance in RMS complex conjugate. Okay, so it's V times the complex conjugate of I, these quantities being for your impedance. Now I have a handout that shows, in fact, we can look right here. See, this handout shows how with this definition of complex power, okay, and again a lot of algebraic gymnastics here, that you can show this key bottom result, that with this definition of complex power can be shown to be equal to I squared R plus J, oops, made a mistake here, let's see, here we go. Okay, complex power is I squared R plus J I squared X. And we just finished seeing that I squared R, that's P average, right? That's equation for P average. And I squared X, that's reactive power Q. So you see, the reason why we make up this power, this complex power, and give it this definition is because it leads to a form where you can represent P average and Q, which are actual powers that you can measure. Well, you can represent them in a right triangle, just like you do impedance with R and X. So you remember from previous discussion that impedance is resistance plus or minus Jx, right? Okay, so you have the impedance triangle, here's your theta Z, here's Z, R is the adjacent side of the right triangle, X is the opposite side. Well, similarly, S, now I didn't show it here, but you could also have a minus Q. That would be a Q for a capacitor, where plus Q is Q for an inductor, just like plus X is inductor, minus X is capacitor. But you see, just like impedance is a complex quantity that I can show as a right triangle, the impedance triangle, well, complex power S is a complex quantity that I can show a right triangle where the adjacent side is P average and the opposite side is Q. Okay, well, I think I'm going to end the video at this point, and then we're going to pick up and talk more about the power triangle and also what power factor is good for.